Excuse me, sir.
Yeah, is the session done? Statistics?
Yes,
Yes,
sir.
sir.
Yeah. Okay, all right. Then let's get started with this. Yeah, is my screen visible? I suppose so. And we'll start. All right. So from week 5 to week 8, the general theme of the syllabus is to deal with functions. From week 1 to week 4, you have seen certain classes of function like polynomials, quadratic functions first, and then generalized to polynomials, how to draw the graph, analyzing end behavior, and all that. Now we'll talk about functions in general. We will look at a specific class also, like exponential and logarithmic functions. And then we'll start dealing with functions, properties of functions like continuity and differentiability, and how it helps us to analyze the functions even more, even better. All right. So throughout the session, we'll be dealing with one variable functions, meaning the functions in general, you can define a function from any set to any set, but the functions that we'll be dealing with will be functions whose domain is a subset of R and whose codomain is also R. So to every, as is the definition of a function, you know that this means that to every element of the of D, you associate a real number. If you want to look at it from the relation perspective, you know that every function is a relation with certain additional properties. So, but what is a relation? A relation is a subset of A cross B. In this case, it will be D cross R. So when you're given a function, there is an obvious candidate of what is called the graph of a function, which is you just plot the relation as a subset of R cross R. For example, if I have f of x is equal to x plus 3, the domain is R, the codomain is R, and this is a straight line, as you know, which passes through 0, 3. Right? So this is the graph of the function. You just pick all the points in the domain and look at the points x comma f of x, and then you plot them on the coordinate plane. What you obtain is called the graph of the function. By the
Sir, I
definition
have
of
a
a
doubt,
function,
sir. Sir,
yeah.
suppose if we want to find the cardinality of this graph and we plot the line using 2 points, then what is the cardinality of this graph? 2, is it 2, sir?
So cardinality of a set means the number of elements in the set. So usually the domain is infinite. So the cardinality will be infinite. Are you referring to something else's cardinality, perhaps?
Cardinality of the graphs that we build using the points, sir. This graph,
So
x of f of x.
cardinality means number of elements in the set. Now, cardinality of, let's say, A is equal to number of elements in the set. So let me write it explicitly. Number of elements in A. So cardinality of a graph. So the graph is also a set. So you can talk about its cardinality, but that is infinite.
We had assignment questions in that I was confused as to what is a cardinality. That's why, can you explain with an example, sir?
Can you give me the question, the specific question?
Okay, sir, I will show it at the end, sir.
Okay, all right. If the domain itself has only finitely many points, then you can talk about its cardinality. If this is not too confusing to you, let me say that this is actually in bijective correspondence with the domain itself. So its cardinality is the same as the cardinality of the domain.
Okay, sir.
But the domain itself, more often than not, will be having infinite elements in the domain. So in that particular question, maybe it was just a 2-element set and the function was just something which had the graph also consequently had only 2 elements. In that
Yes.
case, cardinality equal to 2 makes sense.
Okay, sir.
So yeah, unless you give me the specific question, I cannot say more than that. So if you can find it, it'll be
Yes, sir.
nice.
Yes,
So
I'll show it,
we
sir.
can, yeah. All right. So by definition, a function, so let's continue now. So by definition, a function associates to each element of D a unique element, meaning one element is not mapped to multiple elements in R. One element of D is not mapped to multiple elements in R. But that does not prohibit the happening of two distinct elements of D going to the same element in R. If you look at it just as a mapping between elements of sets, so this sort of situation cannot happen. The function itself prohibits such a thing, but this can happen, right? Multiple elements can go to the same element, can be mapped or can be associated to the same element. And functions for which that does not happen, we call them one-to-one functions. The name is self-explanatory. Sometimes it's also called injective, interchangeable. Both mean the same thing, which says that in addition to the fact that every element is mapped to a single element, it says that no two distinct elements are mapped to the same element. Meaning, if I have a distinct pair of elements, f of x1 and f of x2 have to be distinct as well. Okay, so such functions are called one-to-one functions. Now, using the graph of a function, we can detect whether a function is one-to-one or not. So that is the next thing. So the graph is just, as we were saying, the collection of all points in R2 of the form x comma f of x, where you vary x in the domain. Now there are two tests, graphical tests, to detect whether a relation is a function, and if it is, whether it is one-one or not. So let's take a couple of examples, right? Any subset of R cross R is a relation, but is it a function? To answer that, let's do the following. Let's take a particular example. Let's take something like this. If we want a different color, let's do that. So is it possible that this is the graph of a function? What is the answer?
No.
The answer is no. And why is that?
Vertical line test.
Because for
Yeah, so
same value of x, it has two different value of y.
So
Yes,
there is a line, even one line is enough. All right. So there is, in this case, there is one line. There are many choices of lines. I've just drawn one particular one. So look at these, the points where this vertical line intersects the graph. What would be the coordinates of such a point? So suppose this point is at first coordinate x naught. So this would be x naught comma f of x naught if this was a graph of a function. This would also be x comma f of x naught. And this would also be x naught comma f of x naught, right? But you know that f of x naught is a unique thing. It cannot be three distinct things. So that's why we have the vertical line test, which says that given any subset, if there is a vertical line which intersects the graph in 2 or more distinct points. So over here, there are lines which intersect it only once, vertical lines, but that's not the thing. Even if there is one which intersects it multiple times, then this cannot be the graph of a function. Now, if the vertical test is successful, we can ask whether the function is 1, 1 or not, injective or not. So to do that, we will do something called the horizontal line test. Just like we drew a vertical line and checked whether it has multiple intersections, we'll do the same thing with a horizontal line, right? So this time,
It is also
let's
used
do
to
some.
it is also used to check the inverse of the function.
Whether the inverse exists, yes, it can be used. But then
Okay,
to compute the inverse, you'll have to do the computation.
okay.
Is this a function? Well, assume that
Yes.
this continues properly. And then if yes, is it 1 to 1? Is this a function?
Yes.
It is a function, but it is not one to.
It's not a one-to-one function.
Underline for different value sets, we get the same value of 1.
Yeah. So if I draw this horizontal line, now look at what would be the coordinates of these points. So suppose this is x1, f of x1. So that is this point. And then this point is x2, f of x2. Since this is the graph of the function, every point will be of that form. x3, f of x3. All of these things have clearly distinct x coordinates. But what about f of x1, f of x2, and f of x3? They are all at the same height. Since you're drawing a vertical line, it's at the same height. All the points since you're drawing a horizontal line, all the points on that line have the same second coordinate. So you have f of x1 is equal to f of x2 is equal to f of x3. But clearly x1, x2, x3 are distinct points. So clearly this is not a one-to-one function. More generally, if you have a horizontal line which intersects, even one horizontal line is sufficient to conclude that it is not 1, 1. If there is a horizontal line which intersects the graph in 2 or more points, even 2 is sufficient. In the example, we had 3, 2 or more distinct points, then the function is not 1 to 1. All right. Is what the graph of a function means and what are the graphical tests? Is this clear?
Sir, will you please repeat them?
So if there is even one horizontal line such that it intersects the graph of the function in more than one point, then the function is not 1 to 1.
Okay.
Okay, so that's what is written over here also.
Okay.
So as for the vertical line test, even if there is one vertical line which intersects the graph in, I won't call it a graph of a function because it's test for a function. If you have given an arbitrary subset of r cross r, and then if you plot it on the plane and you find a vertical line which intersects that graph in 2 or more points, then that cannot be a function. All right. So now, talking about one-to-one functions, one of the functions that we will focus on is what is called the exponential function. In general, you can pick any positive number which is not equal to 1 and raise it to the power of x, that is called the exponential function with the base a. And in particular, if a is equal to e, the Euler's number, which is the definition of the Euler's number is not all that significant, is not addressed in the course. It is very significant, actually. But we'll not see how it is actually defined classically. We'll just consider the case when a is equal to e and call that the natural exponential function. All right. Now, depending on the values of a, the nature of the graph of the exponential function with base a will be different. So what do I mean by that? You are allowed to take a in this interval, anywhere from this interval, and you can define the function f of x is equal to a to the x, right? But it has a different behavior when a is in between 0 and 1, and it has a different behavior when a is greater than 1. There are some things which are common, there are some things which are not. Let's see what happens. Right? So what happens when a is in between 0 and 1? So at x is equal to 0, so suppose f of x is equal to a to the x, and a is in between 0 and 1, it doesn't matter what a is. If x is equal to 0, then f of x is equal to 1. So you have this point 0, 1, which is always on the graph. The exponential is always a positive number. So the graph lies always above the x-axis. And there is no point at which a to the x is equal to 0, right? Now, if I take, for example, half, just to get an idea of what happens if I do half square? It becomes 1 by 4. If I do half cube, it becomes 1 by 8. It goes smaller and smaller, and it approaches 0. So the nature of the graph as we approach infinity,
it will be decreased.
it will be decreasing. And on the other hand, if I have half to the power, let's say minus 1, it is 2, right? Half to the power minus 3 is 8. So on the other side, it keeps increasing. So roughly the graph looks something like this. This is the nature of the function when a is between 0 and 1. But what about the other case? When a is in between 0 to infinity, a is in between 1 and infinity. And this is actually also the case where for the natural exponential, because e is equal to 2 point something. So here, what we will get is, once again, 0, 1 is a point on the graph. That doesn't have anything to do with this being greater than 1 or less than 1. But as I decrease the value of x, as x tends to minus infinity, the exponential goes to 0. And on the positive side, it keeps increasing. All right. Now, of course, what happens in the case that a is equal to 1, even though we don't define the exponential function, what is the function? What is the exponential function if it were to exist when a is equal to 1? What happens to f?
Constant.
If a is equal to, yeah, it will be constant. So it will be, the function will be something like this, right? The constant function.
There is no any change in value that.
Yeah, so that's not an interesting function. So that is why we exclude the point 1. Now this is a one-to-one function. We like to talk about its inverse. So first we'll build the machinery needed to understand that. One operation between two or more functions is something called composition. So if I take a function, what I have is I have a set of input values, let's say A to B. For every element over here, I'll get an element over here. And suppose I have a function from B to C. I can act the output of A, and I can act G on the output of A, right? And I'll get something else. So think of it as a two-step process. You take some input, you do something to it, you act it upon, act the function on it, and on the output that is produced, you in turn act G. So this is what is called composition of functions. Of course, when the codomain of the first function is equal to the domain of the second function, you have no problem. But in general, this might not be the case. And when is the composition defined is an important question to address. So here I've written, given two functions f and g, the composition of f with g. Strictly speaking, we should say whenever it exists, and then write this, because g of x may land in something which is not in the domain of f. So we can define the composition only when the range of G is a subset of the domain of F. To see this, let's take up an example. So let's say f of x is equal to sin x and g of x is equal to square root of x. Which of the compositions is defined and which is not? Is f of g defined or is g of f defined?
F of G will be defined because G of F, I think that.
So I need to tell you what the domain for this thing is. You can consider this R to R, G is from R plus, or let me just write it as 0 to infinity to R.
Then it will be F of G can be defined.
F of G can be defined. What is f of G? First you do G, which means you do f of square root of x. And square root of x is a positive number. F takes any real value, so that's fine. I'll get sine of root x.
Yeah.
But what is the problem if G of f?
It will
If
be
we try to
under
compute something like that, so I can do G of
sin x.
sine x.
It will be under root sin x.
It is square root of sine x. This is not always a well-defined real number.
Yeah, it may be.
Right. So for example, G of f of minus pi by 2. If you try to compute, this will not be a real number. So this cannot
Yeah.
be defined. So
Yeah,
f of
and
g can be defined.
G of F cannot be defined because
G of f cannot be defined. As it is, it cannot be. But what if I choose a subset of R as the domain for my function f? Can you give me a candidate subset? Let me write that question down. give an example of a set D in R such that if F is defined on D instead of all of R, if I define F only on D, then one can define U of F. Can anyone give me an example of one such domain?
Can we use that in 0 to infinity? That
So can we have D is equal to 0 to infinity?
yeah, it may without including infinity. That
Is there a problem with this?
I think
Or
that
is it okay?
I think that it is okay, sir.
Okay. How would we do G of F of, let's say, 3 pi by 2? That's a positive number. What are we going to do?
Then under root it will be under root sine 3 pi by 2. That it may occur any problem. That's
Is this a problem?
no, it can be defined.
What is sine of 3 pi by 2?
It is 227 sine 270.
Yes. And what is that?
That is
-1.
1 minus
it will be. I think so that
So is it okay to just do D is all positive numbers?
no.
This
no.
will not work, right?
Yes, yes, sir. It will be.
So let's draw this graph of the sine function. And let's see. It's something like on the other side, I won't draw much. Right? So which parts of the domain are okay? So this point is pi. This is 2 pi, and then it is 2 pi periodic. This is 0, of course. So you want the image of your first function, for which we have drawn the graph, to be positive, because the domain of your second function is the set of all positive numbers. So can you give me an interval now, which works?
It will be at
0 to pi.
So that works, right? D from 0 to pi will work. Why will it work? I'm not saying this is the
One.
biggest possible interval where you can define it, but this is one candidate which will work.
yeah. It is
Works.
one of the subset. It will be.
Yeah, because F restricted to D, if you don't know this is fine. It just means that you're taking the domain to be D instead of whatever is originally defined. F restricted to D is non-negative. If you want the largest possible thing, then you'll have to do all of n pi or 2n pi, maybe 2n pi plus 2n pi to 2n plus 1 pi. You take all things like this and take all of their union. Right, so that's not required. The question just asked for give an example. 0 to pi works. You could do
Then
2 pi to 3 pi.
yeah, then it will become.
So the point is that in general, to define, in this case, we said g of f, we need range of f to be a subset of domain of G, right? So maybe we'll just put this over here. This is the condition. So you may be asked questions where you have to find the domain for f such that the composition is well defined. What would you do? You find the domain such that the range sits inside domain of G. Just like we did over here. Initially, we saw that the domain is not such that the range sits inside the domain of G. So we took a smaller set, a subset of the domain, which satisfies this condition. When restricted to D, the range of F is 0 to 1, both of them included. And hence, the range of F is a subset of domain of G. So what you require is actually this. Whenever you're looking at compositions and well-definedness of compositions, this is the thing that you're going for. All right. So that's what is written over here. Note that the domain of f of g is the subset of, okay, here, there we had written g of f, so it is reversed. But the domain of f of g is the subset of the domain of g, which maps to the domain of f. All right. So that's about the definition of composite functions. Now, a very natural question to ask when you are encountered a function is whether you can undo the process. As in, one way to think about functions is you have a set of elements, and then you do some operation and you get an answer. So if you know the answer, can you get back the question? Or if you know the output, can you trace it back to the input? This is a very natural question. So clearly here one-to-one starts playing a role, because if you have a function that is not one-to-one, let's say you have 2 of the elements going to something and another 2 of the elements going to something. So if I want to write a map between B to A, so if I have a function from A to B, if I want to write a function from B to A, which assigns to every output of the original function its input, when I write the reverse function, clearly there is a problem. I cannot write it as a function because each of the elements, when seen in the reverse direction, when in the forward direction, it's a function. Every element is mapped to only one element. But when you see in the reverse direction, these 2 elements are mapped to 2 elements. So you cannot define.
So
the
in that
inverse map.
basically, if the domain of the first function become that after range, and the range of that function become domain.
Sorry, are you talking about this inverse of a function itself?
Yes.
Okay. Yeah. So right, if you want to write the inverse function, your the range will become range of f becomes the domain of f inverse.
Yes.
Yeah. All right. So, but whether we can do it in the first place depends on whether the function is one-to-one or not. If it is not one-to-one, there is no unique way to associate to the output and an input variable, right? So,
First
we
of all,
want,
we have to check that if the function is one.
Yeah. So when a multiple, when some element over here has multiple preimages over here, you will run into problem. So if the function is one-to-one, there is a nice way of defining an inverse function, which simply is defined by the law that if you take an element of the range, I will just, as I associate it with its input in the original function. That is what is called the inverse function. And as was pointed out and as should have been written, the domain of F inverse is equal to the range of F. So we are just asking for one-to-one. We are not asking for onto-ness. So what happens is some elements of B might not have any pre-images. So we want to discard those guys, right? So let's say, let's take an example. And let's say I want to find the inverse of x square, right? This is not a question. This is just, let's just analyze this. To R f of x is x square.
Sir, can I get the PDF of this division session?
You will get this. This will be available on the portal where you find all the live session documents. Live session, what is it called?
Under which tab?
Under supplementary contents, you have this.
Okay, sir. Thank you.
Suppose, sir, that if we take the simple example that is fx is equal to 2x plus 3, then it will be or not?
It will be, okay, we'll also see that. Now, first, let's resolve f of x is equal to x square.
Okay,
There. So if I want to write an inverse map from R to R, let's say, if at all this is possible, there are multiple problems, right? I'll just write a couple of values. I cannot write all the real numbers over here, but I'll just write some of the integers and what they are mapped to. What is -3 mapped to?
it will be 9.
Yeah, right. So I'll write only the square numbers 0, 1, 4, 9. And there are many others. So there are all real numbers. I'm just taking the part of the thing that is relevant
Obviously,
to my discussion right now.
that -3 and 3 both will goes to that 9.
Yes, and -2 and 2 will go to 4, -1 and 1 will go to 1, and 0 will go to 0. Now, if I want to define the inverse, it's not possible because there are some elements which have multiple pre-images. Suppose if I want to say what is f inverse of 9, there I have two choices. When I look at 9 and look at what it is mapped to, it is 3 or
it will
minus
be
3.
-3 and 3. That's
Yeah, but instead, I'll now define this function from 0 to infinity to R. So it's just on the positive real number, non-negative real numbers. Now you see it's a 1-1 function, right?
Yeah, there is a single output.
Sir.
There is a single output for every input. But even now, I cannot define it from R to R because what would be f inverse of, let's say, -2?
Yeah,
Is there any element, any positive number whose square is -2?
No, there is nothing
No.
else.
Nothing, right? So when we define the inverse, we define it on range of f, not the entire codomain.
Yeah, we have to use that range. Their range and domain will be.
Right. So what is the range of f? Even though this is just R, range of f is 0 to infinity. So the inverse can be defined from 0 to infinity to 0 to infinity. The codomain for the inverse function will be the domain of the original function, right? Because your original function was something like this. Now you're doing the inverse of it. So what is f inverse of x in this case? what is the element that is mapped to X? So let's say what to get examples. What is F inverse of 3? What element squares to give 3?
Uh,
Root 3.
under root 3.
Right? Now you know what to say
Root X.
to this.
Root X.
Square root of X. I can do this because my domain I have chosen in such a way that it is only positive, non-negative real numbers. So square root of X makes sense. It is also a positive number. All of this is well defined and we are good to go.
Yeah.
In general, so there was one more example that was suggested. Can you repeat, please?
That is 2x, 2x plus 3.
2x plus 3. Okay. First of all, is this a one-to-one function? Can we define the inverse? So what is your let's look at it as a function from R to R initially. If necessary, we'll make changes. Is this a one-to-one function?
Yeah, in that R to R it is a 1, 1.
Right? It's a straight line. Of course, if you draw any horizontal line, it will intersect it only once.
Yeah,
That's one way to look at it.
Only
And
single
the other
outputs.
way to look at it is if I look at two different, is it possible for two different inputs to have the same output? No, because if the output is the same, it forces the input also to be the same. So this will become x1 equal to x2. So the only way f of x1 is equal to f of x2 is if x1 is equal to x2, and that is the theoretical way of proving injectivity. Now this is injective, we are good. So we can also, what is the range of f? F is injective. That's also good. What is range of f? In order to define the domain of f inverse, we need to know what the range of f is. What is the range of a straight line?
Is also all real numbers.
Yeah, range of f is also R. If this is not clear, you just look at any real number R and look at x is equal to R minus 3 by 2. Okay, so R minus 3 by 2 will be mapped under this function to R, which is also another way of saying this is this. Okay, so this happens for every real number. So every real number has a pre-image and a unique one. So this is actually what you call a bijection. It is injective as well as surjective. But let's go back to doing the inverse calculation. F inverse is a function from range of f, which we have calculated to be R, to the domain of f, which we also have to be R. Now, what is the formula for the inverse?
That it will be y minus 3 by 2.
Yeah, it will be y minus 3 by 2. But let's see how we get that. So suppose you have this to be some y. Okay. I'll try to write it in terms of x itself. So it'll become x minus 3 by 2. So here the property of the inverse helps you. So the definition itself says, and this is how we have motivated it as well, that it's a function in the f inverse is a function such that f inverse of f of x is x and f of f inverse of x is also x. Meaning if you go forward and then backward, you'll land at the same point. You look at the input, you get the output, and then you come back to the input. So this is the identity map. The composition of f inverse with f as well as f with f inverse, both of them are the identity function. So So what do we do over here? We can do f on both sides. I get f of f inverse of x is f of y. But what is f of f inverse?
Will be
X.
It's just x. And f of y by definition is 2y plus 3. So what would y be? If I rearrange, I'll get x minus 3 divided by
by
2.
2. That is.
But what was y? Y was by definition f inverse of x, right? So f inverse of x is x minus 3 by 2. So yes, 2x plus 3 is invertible, and the inverse is f inverse of x is x minus 3 by 2. Is that okay?
Yes.
So you can think of the kind of questions that you can be asked over here. You can be asked a domain for a function for which the inverse exists, or to compute the inverse, or to compute the range of the domain of the inverse
Sir,
function, which is
if
just,
excuse me, sir.
yeah,
If we take that the function like x to the power 3 by 2, then from R to R,
f of x is x to the power 3 by 2.
3 by 2 from range R to R, that domain.
Well, R to R is not good, right? Like when you're doing exponentiation, it's better to restrict yourself to positive side, because minus 1 to the power 3 by 2, what does that mean?
Yeah.
Right? Because you can't have square root. So just for the well-definedness of this function itself, this is better. Otherwise, it will not be well-defined on negative numbers.
Yeah, except negative number.
Yeah. So I'll just define it on non-negative real numbers. Now, is it a 1-1 function, first of all?
I think that it will be that. Yeah, it will be 1 1.
Why will it be 1-1? So once again, you can look at this. If the image of two inputs are the same, then I can square this to get x1 cube is equal to x2 cube.
Yeah, then we can say that its power is cube. Then we cannot say that input is same as out. It will be performed
Yeah.
at -1 also and +1 also.
No, but for cube, it is okay, right? Cube root is unique.
Yeah.
So here x1 equal to x2 will happen. So it is actually injective. Is it clear why is it injective?
Yeah, it will be clear that.
Yeah. What is the range? What is the range of this function? Anyone?
0 to infinity, sir.
It has to be positive, right? If you
From
cube a
R,
positive number, it is a positive number. If you take its square root, it's also a positive number, right?
Yes, sir.
Is that okay?
yeah, sir.
Range of f is 0 to infinity. So I can define f inverse from range of f to domain of f. So this is range of f. Even though they look the same, it is important to note that this is how we get it. Range of f to domain of f. And suppose your f inverse of some number x is y, then you will have x is equal to f of y. Once again, by operating f on both sides of this. So x is y to the 3/2. So how do I recover back? How do I get an expression for y?
Yeah, it will be cube root then.
Just cube root. It will be 2/3, no?
Yeah.
So this is your expression for f inverse of x. Okay.
Okay, sir.
Sir, for the inverses of a function to exist, the function should be both 1, 1 and onto. Am I right, sir?
Not necessary. Onto is not necessary. If it is not onto, what you do is you, for the inverse, you just define it on the range. That's what we have been doing over here. So over here, the original function itself is not onto. So when I'm defining the inverse, I'm just defining it on the range instead of the codomain.
But if it's asked as a question that for this interval, if both the functions are inverse of each other, like that, if they ask the question like that, then what is the answer for that?
Let me just quickly check what the convention used is. Inverse functions. I mean, I don't think you'll be asked questions like that.
Okay, sir.
So even this definition is what is given by the prof also. Given a function, the inverse is a function which satisfies this, and you only require it for all x in the range of f.
Okay, sir.
Okay. All right. So now we come to the logarithmic function. So this addresses the question of, so we did see that this exponential function, to whatever base you take, as long as the base is positive and not equal to 1, is a 1, 1 function, right? The kinds of graphs that we saw, if a is greater than 1, it was something like this, and if a was less than 1, it was something like this. It had the different behavior. But in either case, it's a 1, 1 function. By either by horizontal test or by some other method, you can see that these are 1, 1 functions. So what is the inverse of the exponential function? And the answer to that is the logarithmic function. So what does it mean to say that logarithmic function is the inverse of exponential function? So let's just take powers of 2. You know that 2 to the power 3 is 8. 2 square is 4. All right. Now, if the question is, if you want to know to what power should one raise the number 2 to get, let's say, 6. So I want to know what the answer to this question is. It's definitely not 2 or 3 or any integer, because for integers we know the answer.
Yeah, it will be some that fraction or that some not.
It will be something in between 2 and 3. That is intuitively clear.
Yeah.
But what is the exact value? So what you're asking is, if I consider this function f of x is equal to 2 to the x, right? So I know that over here 2 goes to 4, 3 goes to 8, and there is this 6 guy in between. Is there something over here for which 6 is the answer? So if 6 is the output, what is the input? In other words, what is the inverse of 6?
Yeah, it will be definitely in between 2 and 3 then.
It will be in between 2 and 3, but what is the exact value? That is exactly what we call log 6 to the base 2. The power to which 2 needs to be raised in order to get 6, or under the exponential function, what should be the input so that the output is 6? Or what is the value of the inverse of 6? So that
Yeah,
is
yeah.
the motivation for no, it's not the motivation, but well, logarithmic function is just the function inverse of the exponential function, right?
Yes.
Once
Yeah.
again, for the logarithmic function, we have a base and a variable. So the base is fixed so long as it is positive and not equal to 1. The same conditions as we had for the base of the exponential function. And it is defined as the inverse of the exponential function. Now, the inverse of the exponential function exists because it is 1 to 1. And what was the range of the exponential function? Do we remember?
Zero to
Positive.
infinity.
Yeah, it's strictly positive. It never becomes 0 also. So the range of the exponential function is, of course, the domain for the logarithmic function. So the domain for the logarithmic function is
It will
0
be
to
range for-
infinity, 0 to 0 not included, positive real numbers, strictly positive real numbers, right? Now, using the exponential, using the fact that this is the inverse of the exponential function, one can derive certain properties, and these properties you will have to use in to solve what are called logarithmic equations. Usually you will have many things in terms of logs, log this plus log this is equal to something, and there will be some variables which you have to solve for, and using these properties, and okay, I've not written the uh, reversing the base and the exponent thing, but I hope you know that also.
Yeah, yeah.
This is 1 by log MA, right?
Yeah, yes.
And yeah, you can change the basis by just taking the
By
ratio.
reciprocal.
Yeah. So all of these are properties of the log function, which can be used to solve the logarithmic equations. I think there was someone who in the last session wanted to solve some logarithmic equation. We'll take particular problems at the end if we have time. For now, I'll just state these properties and we'll move to the next topic, which is that of calculus. So now that we have looked at certain specific class of functions, we'll deal with general functions now. And to understand functions, we need to understand sequences also. Now, what is the sequence of real numbers? A sequence is what the English word sequence means. It's just a set of numbers which you can write down as A1, A2, A3, and it's an infinite set. Easy examples of sequences are an is equal to 1 by n, an is equal to minus 1 to the n. You can do whatever. You can have a constant sequence. You can just say an is equal to 2 for all n. That is also a sequence. So it does not have to have different, necessarily distinct values for each n. Over here also, you'll see that there are only two values that the sequence takes. And in this case, it is actually a constant sequence. So that is what a sequence is. This sequences will be used later on when we discuss limits. So that's why we are introducing this. And a subsequence is if you have a sequence of numbers, let's say this, you can choose to skip some of them and just pick some of them. That in turn will become a sequence, right? You need to pick infinitely many of them. So such a thing is called a subsequence. Now, what is interesting is the limit of a sequence. The mathematical definition of a limit of a sequence is not this. It is a little bit more involved because here we are just saying it comes arbitrarily close, but that level of detail for this Math 1 course is not, we are not going to go into that level of detail. We are just going to say that it converges to a real number a if it comes arbitrarily close to a as n increases. For example, take an is equal to 1 by n. As n increases, what happens to the value of an?
Then it will be close to that 0.
Zero.
Close to 0. You can make it as close to 0 as you want, right? You can have so if you say that I want some,
Basically, we
I
can say
want all
that it approaches to that 0.
yes, it approaches to the 0 and uniformly so. So in this case, so let's say I want it to within 0.01 of 0. You definitely have values of n
100 and
for
100.
which, yeah, anything more than 100 will stay within that interval, right? So that will give you a sense of what the classical definition of it is, but we just state it loosely. And to contrast with this, so here we'll say an converges to 0. What about minus 1 to the n?
Then it will shows that 1 then minus 1 minus 1 minus 1 1 minus 1.
It keeps oscillating between two numbers.
Yeah.
Close as you want to one single real number. That does not happen.
As it get that odd number, then it will become minus 1, and it got that even, then it will become 1.
Yeah. But this has a subsequence which converges. As it is, an diverges. Whenever it doesn't converge, we say an diverges, because there is no one single real number to which the terms of the sequence converge to, right? So we say an diverges. And what about if I only pick the even numbered terms of this sequence? That's a subsequence of this sequence. What happens then?
Then it will be continue to that 1 1 1.
It will just be 1. It will be a constant sequence.
Yeah, it
right?
will be constant that.
So that converges. So the sequence itself diverges, but there can be a convergent subsequence. This is just a side note. But to show something converges or diverges, we have certain properties, expected properties. So here we said that a divergent sequence can have a convergent subsequence, but can a convergent subsequence have a divergent subsequence?
No, it is not always sometime, but not.
Okay, let me write that. Can a convergent sequence have a divergent subsequence.
Not at all.
It's not, right? Like you are saying that all terms eventually go to some real number. If you omit some of them, and if you still consider a subclass of those, if you consider a subset of those numbers also, they'll also go eventually to that real number itself. So that's the first point over here. Every subsequence of a convergent subsequence converges.
Yeah.
And then if you have a sequence that can be written as a sum of two sequences, both of which converge, then that sum sequence also converges, and it converges to the sum of the limits. Convergence respects product, scalar multiplication,
Cumulative property.
and then quotient, as long as the denominator is not zero, exponentiation, logarithmic.
Sir, in that whole, their limit will be combined.
What do you mean by limit will be combined?
Suppose you told that an plus bn goes to a plus b, then their limit must be combined.
The limit must be the sum. So if an and bn is eventually, as in if an separately converges to a, bn separately converges to b, then an plus bn will converge to a plus b.
Yeah, then this rule comes to multiply also and divide also.
Yeah. And scalar multiplication also, but there you don't have two sequences. You can think of this as a special case of a and bn equal to ab, because you can take bn to be the constant sequence c.
Yeah.
So you will get that as so this is actually a particular case of this.
Okay, sir. Okay.
All right. So all the operations that, not all the operations, but at least these operations: addition, scalar multiplication, and multiplication of sequences, quotients, exponentiation, and logarithmic, these operations are well behaved for sequences. So the last one is probably one that is very important, which says that if I have a sequence which is sandwiched between two sequences, and both of the extremities, the an and dn, the sequences which bound the sequence of interest, if both of them are converging to the same limit, then the center sequence also converges to the same limit.
Yeah, basically.
Once again,
yes.
Yeah, it's called the sandwich theorem, and this is for
In that calculus also, that yes.
yes. So let's do some. Yeah, this is just a very standard classical example for the same. Does this sequence converge? Right. Instead of doing this, let me give you a more general property, which is a consequence of the sandwich theorem. Let bn, let an and bn, let's just have one sequence. Let an be a bounded sequence. What do you mean by a bounded sequence? Anyone? Any ideas?
I think that there is a
Sequence is either
limitation.
bounded lower bound or upper bound.
There is a
When I
limitation.
say bounded, it always means it is bounded on both sides. So,
Can we say that it is closed to a limit between brackets? Square brackets.
sorry.
For bounded sequence, can we say that there are limits in that square brackets?
The limit, so a bounded sequence need not be convergent. So you can't talk about the limit unless you know it's convergent. I'm just saying it's a bounded sequence.
Okay.
Sine function,
Right, so
sine or cos function.
yeah, these are bounded sequences. Even more trivially, -1 to the n that's a bounded sequence, right? Which does not converge, right? Because it is between -1 and 1. Of course, I can put this as -1 and 1, and -1 to the n will satisfy this condition.
Yes.
Right. Then the sequence Bn is equal to An by n converges. Can you see why?
Yeah, because there is a sometime I think that constant value that gives.
So just by definition itself, you have An to be bounded in between this and this. So if I divide by n, what I will get is this. So what happens to this part as n goes to infinity?
It will be that 0 something approach.
This also approaches 0, right? It's just a constant by n. 1 by n
Yeah.
goes to 0. So a constant times that also goes to 0. So
Yeah,
both
Then
extreme
the then the
ends.
center one will be also that.
Yes.
These are the consequence of that sandwich. Yes.
Yeah, this is a consequence of sandwich theorem. So whenever you have bounded sequences, and then if you have a sequence that converges to 0, more generally, you can use this to conclude that it converges. Over here, I should have had another slide. I'll let you guys know that there are some limits that you need to know, which if you don't know, then you can't really derive it. There are some things like this. Say some standard sequences. Go back to the props lectures and look at. There are, I think, 3 or 4 ones which it is good to commit that to memory. That 1 plus x to 1 plus x by n to the whole to the power n converges to e to the x, and so on. So there are these some standard sequences. Those standard sequences plus these properties should be enough for you to solve any problem that is given. Sometimes you'll have to convert a given trigonometric expression using the laws of trigonometry that you know, sine 2x is 2 sine x cos x, and so on. Sometimes there is an expression which involves a lot of trigonometric terms given, and then there you have to carefully play around with the identities, trigonometric identities, and bring it to a certain form where some part of it can be solved by sandwich and some part will just go to 0, for example. If I'm talking very loosely, but sometimes you'll have to do such manipulations to get it into a desired form where you can use one of these properties. It would be better to give a robust example towards the end. If I can come up with something, I'll let you know. But let's move on. Now that we know limits of sequences, we'd like to know limits of functions. Now, limits of functions is naturally leads to continuity. So the limit of a function is, suppose I have some function. What is continuity? Continuity is roughly, very, very roughly speaking, I would not want to have any breaks. So when would there be a break in the function? So if the behavior of the function as I approach a certain point is different from the nature of the function at the point or to the right of it. If the behavior of the function to the right and to the left are different, then there is a jump, there is a break. This is possible. This is one way in which discontinuity can happen. So we'd like to formalize what the notion of the limit of a function is, and then demand that limit of a function is equal to the function value, right-hand limit, left-hand limit. So here we have the definitions for the right-hand limit as well as the left-hand limit. As I was saying earlier, if I have a function, I look at the behavior of the function to the left of it. And when I say I look at the behavior of the function to the left of it, I consider the sequences which approach the point from the left, meaning an is less than a and an converges to a. So once again, if I draw the diagram, if I have some point a over here, I have the function to the right and something else to the left. Now I look at a sequence of points that converges to a, and I look at the corresponding function values. That is another sequence, right? F of an is a sequence. If an is a sequence, f of an is a sequence. I demand that if an goes to a, then f of an should be a convergent sequence. It might converge to something. And this has to happen for all sequences. Doesn't matter what sequence I take, as long as it is to the left of a and it converges to a, its corresponding function sequence f of an has to converge to a single real number L. All right. So if such a thing happens, then we say that the left-hand limit exists, and we call the left-hand limit as L itself. All right. So the same thing for the right-hand limit. All right. This is the definition of the limit. Just to give you an idea of what the extreme case is where you can prove the discontinuity of a function or non-existence of limit of a function, let's consider the following example, f of x. It's a function on non-zero real numbers, let's say on r minus singleton 0. Does this have a limit, right-hand limit or left-hand limit? We approach 0. Right. Does f have, let's just talk about LHL now, left-hand limit as x approaches 0, which also we denote by x goes to 0 minus. Even if you can't justify, what is the answer? Do you know?
Yes, sir, it exists. Suppose if we take sine of 1 by 0.99, can we take it like that, sir? Point minus.
So we are approaching 0, right? So if you do something like, if you look at this, and so on, what would be the nature of this function? It would be sine 100, sine negative, of course, negative sine 10 to the 3, and so on, right? So is there any pattern to this?
Yeah, there is only power changing.
There is a power changing, but is this sequence approaching some number, some real number?
Yeah, it will be definitely.
0.
Will it approach 0? Does the sine function approach 0 as we go greater and greater values? Will there not always be points any arbitrarily large such that the value of your sine function is 1? And will there not always be arbitrarily large values where it is -1? So when you say it approaches zero, you after a certain point it has to be close to zero. Does that happen? So let's say you consider some this is the sine function, right? As I go closer and closer to infinity, meaning I'm taking larger and larger values, can you see that the function is approaching a certain real number?
Yes.
What
It's
is the
going towards
real
the
number that is
infinity
that
only.
it is approaching?
It's going
No,
to
the function
infinity
value I'm
only, and it's
asking about.
bounded between.
So when I going x goes to infinity, does sine x goes to some number?
Like it ranges between -1 to 1. Between this only, these two numbers, it will fluctuate.
It goes to zero, sir.
It's between -1 and 1, but it's not approaching any particular real number, right? It is bounded, yes, but is it convergent? So
No.
compare this
Yes.
with -1 to the power n. Even this is bouncing back and forth between -1 and 1, but you don't say that this is a convergent sequence.
Yeah, that it
Right?
will be fluctuated.
It's always fluctuating.
Yeah.
So this has no specific pattern. Maybe you can choose a sequence in such a way that it will go to a zero, but this has to happen for all sequences, right?
So convergent sequence are those which approaches towards zero.
To some to a particular real number. It need not be zero, but it has to be some real number. In this case, it is continuously oscillating between +1 and -1. There is no one particular real number is approaching. Now,
So
okay,
then will we say that
let's
it
get
is
back to this problem. Yeah, go ahead, please.
So now will we say that it is divergent then?
This is divergent, and I'll give you a specific sequence which will answer your doubts, hopefully. Consider the sequence inverse of pi by 2, reciprocal of pi by 2, 3 pi by 2, 5 pi by 2, and so on. I'm just taking odd multiples of pi by 2 and taking its reciprocal. So you can write down the general formula for an if you want. But these are just odd multiples of pi by 2 reciprocals. So this is my sequence an. What is f of an? This is an. What is f of an?
1 by 2n plus 1 pi. Sorry, 2 by 2n plus 1 pi.
So an is 2 by
2n
2n
plus
plus
1.
pi.
Okay. Yes, 2n plus 1 pi. 2n plus 1
a1.
pi.
So let's do this. Sine of 2n minus 1 pi by 2. Now, what is
Okay.
the nature of this?
It will be 1. 1 or minus
What is
1.
it for? It will be 1 or minus 1, right? So it will be
Yes.
actually minus 1 to the power
2n
n plus 1.
plus 1. Yes.
F of an is not a convergent sequence, isn't it?
Sir, but it is bouncing between two values. Like we did in the example, 1 or minus 1. 1 or minus 1.
Yeah, so f of a n does not converge, or it diverges. Therefore, LHL does not exist. Right? So what does the existence of left-hand limit require? It says for all sequences an less than a. Okay, so here there's a mistake. Since we are talking about LHL, I'll probably need to take this negative 2. So this is all minus. So you'll probably just get this. Okay, that's okay. Minus. That's a minor point. So for all sequences an less than a, for which an converges to a, we should have f of an to be a convergent sequence converging to L. Is it happening over here? I have given you a sequence such that an converges to a, but f of an diverges. An less than a, an converges to a. So in this case, a is 0, f of an diverges. Is this clear?
Yes.
Yes, sir.
So once again, if you draw the graph, it might be clearer. To draw the graph, of course, I will just draw a very rough graph. You guys go and do it on any graphing software. What happens is, towards infinity, it goes to 0, this function, sine of 1 by x. But then as you go closer and closer to 0, it rapidly oscillates between +1 and -1. So it does not approach any one particular number. The same thing over here also. So here,
Yeah, it will be fluctuated then.
So it will be fluctuating very rapidly on either side as we approach 0. So that limit does not exist. So if you want to say that the limit of this function of a function does not exist, all you need to do is provide one sequence which does not converge. So what is the sequence that I chose? I chose this point, this point, this point, this point. And there are infinitely many of them, right? I can choose this sequence. Let me draw that with black. Because I have infinitely many of them going to 1 and infinitely many of them going to -1, I can construct this sequence, which does converge to any real number just by sequence theory. This is one of the first examples that we see when we talk about sequences which do not converge. While the existence of the left-hand limit requires that for all sequences less than the point of interest, which converge to the given point of interest, the corresponding function sequence has to converge, which is not happening over here. All right. Yeah.
Sir, I have some doubt in some problem questions. So
We'll do that towards the end. Problems we'll do towards the end. Now,
okay.
limits of properties of limits. We'll quickly get through the next if you haven't. All right. Now, properties of limits also is very similar to the properties of sequences, because limits are defined via sequences. And as I was saying in the summary session earlier, that the practical way of establishing that limits exist is not by considering all possible sequences and looking at f of an and somehow justifying that that's a convergent sequence which to the same limit. You have to convert it into a well-known, a combination of well-known functions like whatever we have over here, sums of functions, scalar multiples, products of functions. If you have things like that, then and there are certain functions, certain classes of functions that have limits, like trigonometric functions, polynomial functions. They all behave very well. And if you can write the given function as a combination of those and use one of these results, properties, then you can establish the existence of the limit. And later on, after discussing differentiability, we'll also discuss L'Hopital's rule for when you have a certain indeterminate form. Now, over here also you have the squeeze theorem, which instead of a sequence bounded below and above by two sequences which converge to the same limit, instead over here we have a function which is bounded below and above by two functions which have the same left-hand limit or right-hand limit or the limit. So if the right-hand limit and left-hand limit exist and are equal, that is called the limit. And if both of them have the same limit, then the central function also has the same limit. Whatever example we discussed for sequences, you can make an analogous example for functions also. I think I discussed this also in the summary session. X sine 1 by x you can take and show that this has a limit. Even though this does not have a limit, just sine 1 by x does not have a limit. It continuously keeps oscillating between +1 and -1. X sine 1 by x does, because this x factor will reduce the modulus of it, and it will no longer oscillate between +1 and -1. It will oscillate between +x and -x. And that will keep decreasing as x goes to 0. And this one will actually have a limit. In fact, it will be continuous. We have not seen continuity. So once we do that, we can make that comment. All right. So continuity is now a very natural extension of whatever we have seen. If we have the right-hand limit and the left-hand limit to exist, and the function also to be defined in such a way that it is equal to the left-hand limit and right-hand limit, then the function is called continuous. Visually, you will see that you need to have the function converge to a certain point, and from the right and the left, as well as the point itself should have the same value at that point. So if I have a function which is, let's say, like this, as in over here, at this particular point, I have the function to be somewhere above. Let's say it is f of x is equal to x cube if x not equal to 0. And let's say I just call it some 2 or something, if x is equal to 0. So what would the graph look like? X cube, the graph of x cube, is something like this. But I am removing this point. At 0, I'm saying that the value of the function is some 2. There's clearly a break. There's clearly a jump. In this case, what is happening is the function limit as you approach 0 is 0 from the left as well as from the right. But the function value itself is not equal to the value that either limit approaches. So this is an example where this exists, both are equal, but it is not equal to the function value at that point. Okay. Yeah. Is there any doubt?
You just keep this line, and I would like to say that can you please check at x equals to 1? The function at x equals to 1, is it continuous or not?
This function itself?
Yes.
Yeah, it is continuous. There you don't have a break. So it is x cubed to the left, it's x cubed to the right, and the function value is also equal to 1.
Okay.
Right? So what is LHL in that case? It
LHL
is
is 1.
limit as x as sorry, this is 1 minus.
1 minus, yes.
So it is x cube itself. So you can just directly substitute. Since it's a polynomial, the limits exist. So this is 1. RHL is also similarly 1. And what is f of 1? As per definition, it comes under this. It is 1 cube, which is 1. So everywhere other than 0, it is continuous. Only at 0, there is a jump. So there is a discontinuity.
Okay.
All right. A better or a more standard example of a discontinuous function is the floor function, where you have the graph diagram, something like this. Right, so there, every time the left-hand limit goes to the lower integer value, Yeah, and the right hand limit goes to the function value, but the left hand limit goes to one integer lesser than that. All right, so these are very standard examples to understand continuity. Now, we need something more than continuity to analyze the rate of growth of functions and so on. So for that, we have what is called the derivative of the function. The derivative of a function is the infinitesimal change of rate of change of the function. I made the same mistake over here also, I think. This was there over there also. So if you want to look at the rate of change of the function, what do I mean by rate of change of the function? How much the function changes as I change the input, right? So this h is the change in input. So when I go from a to a plus h, how much does the function change? Increase or decrease or stays the same? That we'll see. So this is f of a. The height is f of a. This is f of a plus h. So I do f of a plus h minus f of a. The change in the output corresponding to the change in input. The change in input is precisely h. I take that ratio, I take that rate of change, and I take the limit as the change goes to 0. And this is what is called the derivative, if it exists. This need not always exist. Yeah.
Suppose I take a polynomial of a very higher degree. Suppose
Okay.
x raised to 1000, or you can consider it very high. So
Okay.
if I differentiate it, I will get a very big value, right?
Yes.
So
You will get
then my slope is-
not necessarily, the slope need not be high though. Yeah.
but why? So it should, is it continuous, sir? If I take such
All
a,
polynomials are smooth, as in they are differentiable.
but
So
if
it need
I-
not be,
okay.
the slope need not be high. Whatever you want to say, let's say x to the 1000. At let's say x equal to 0, I want to create a critical point. What would I do? I would say -1. Let's say just do something like this.
Okay.
Okay, what is the derivative of this? This would be 1000 x to the power
1000 x raised
999.
to 999, yes.
At x equal to 0, it is 0 anyway. So
Yes.
there are points at which it is positive, negative, 0. It
Yes.
has a high rate of growth, but there are also critical points. Right? In this case, only 1, but you can see that there could be a higher degree, very high degree term with a negative sign, which will kill its growth.
Okay.
Eventually, this term will dominate. The
Yes.
nature of the graph will be as such, but it's not that the slope is high everywhere.
Okay, so it remains continuous.
It is continuous, yes. In
If
that case,
if I
it is
say
continuous
R to R.
differentiable.
Okay.
It is continuous differentiable. The derivative is continuous. It is, polynomials are as nice as you want them to be. They're among the nicest class of functions. Right. So back to derivative. This is the definition of the derivative, but the standard identities for standard functions, the derivative of standard functions, it is better to know, and I'm assuming you already do, for trigonometric exponential, polynomial,
Yes.
x to the power n, a to the power of x, and so on. Usually the functions that are given to you will be some product, some scalar multiple, quotient of such expressions, or composition of two differentiable functions. All of these are differentiable, first of all. And the rules that govern the derivative of combinations are given over here. For the sum, it is just the sum as it is. For the scalar multiple also, it is the scalar multiple. For the product and quotient, you have a different rule. For product, you have differentiate the first function times the second function plus the first function times the derivative of the second function. And for the quotient also, you have a an expression which I'm not going to read out loud. I'm sure you already know this. And for the chain rule also, you have enough practice by now solving problems using this, I'm assuming. And we have
Yes,
also
sir.
taken this similar problems in summary sessions as well as solve with us sessions. So unless someone explicitly wants me to solve some problem of
Sir,
this
there
sort,
is,
I'll move ahead.
excuse me, sir.
Yeah.
There is a question of continuity. I do not able to solve it. I was put it and on the chat
Okay.
section.
There's just a couple of slides. Let me get through that, and then we'll take a look
Okay,
at it. Is
sir.
that fine?
Okay, sir. I will be put it in that chat.
Okay. If you paste it in chat, I usually don't look at it. If you can say it out loud, it'll be better. I'll let you know once the slides are done.
Okay, okay,
I'll
sir.
let you know. You can just say it out, and then we can discuss. All right. So yes, back to L'Hopital's rule. Now that we know differentiability, there is a very strong rule called the L'Hopital's rule, which allows us to compute the limits of functions which are written as the ratio of two functions. And it works only when both the numerator and the denominator are differentiable, other than possibly at the point of interest. Now, and you should have a 0 by 0 or an infinity by infinity form. Then what you can do is differentiate the numerator and the denominator separately, calculate the limit. If the limit exists, then the original function also has that same limit. So saying all this is not as effective as doing an example. So we'll do one, rather straightforward one. F of x is, let's say, this by this. This might work, yeah. So can you check if L'Hopital is applicable over here? Of course, this is x not equal to 0.
Yes, sir. It will be applicable.
And calculate the limit.
Will be 0, I think, sir. That Fifi.
Is it 0?
In that numerator, it will be 0 then, obviously. That.
But the denominator is also going to 0.
Yes, that.
Can we use that f dash x upon fx? No, but here the angles are different.
See, first of all, is the numerator and denominator.
No, sir. If we use that L'Hopital's rule, then it will also
Yes.
goes to that 0.
Okay, let's do that. So here my f is f1 by f2, where f1 of x is e to the x minus cos x, and f2 of x is sine 3x. What is f1 prime of x?
It will be e to the power
E raised
minus
to
x
x minus
plus
sin
cos x
It should be this.
plus
No?
sin x. Yes.
plus
yes.
sin x. Yeah, yeah.
Sin plus sin x.
And what about this?
3 cos 3x.
3 cos 3x. Yeah.
What about taking the ratio?
That it will be 1 divided by
Yes.
Let's write it as it is. Now what
Yeah.
happens when you go to 0?
1 divided by 0. 1 divided by 3. Sorry.
Yes. 1 by 3.
Yeah.
This is not equal to 1 by 3. The limit of as x
Limit
goes to
x tends
0.
to 0, it will be that.
So the limit of the expression after differentiating the numerator and the denominator exists and is equal to 1 by 3, right? I just
Yeah,
did the
yeah.
substitution and here it works. After I differentiate, of course, initially the substitution doesn't work because it gives you 0 by 0.
Yeah, it will be formed that 0 by 0 form.
Therefore, limit as x goes to 0, f1x by f2x, which is e to the x minus cos x divided by sine 3x is equal to 1 by 3.
So, sir, we can say that in the function in which we use L'Hopital's rule are removable discontinuity functions. Removable discontinuity functions.
Yes, yes, yeah. If the limit exists, then it's a removable discontinuity. As in, if you talk about discontinuity, first of all, it has to be defined at that point also. And what did you define it as in the first place? Right. So if that is arbitrarily, it can be extended to a continuous function. You can say that.
Yeah.
Right. All right. So the last two things are related and they're the most fresh topic. So I'm hoping people know this already, that this is just the slope point formula for the data that is a comma f of a. What is the line that passes through a comma f of a with slope f prime a? It's precisely this. And graphically, if I have something like this, if I look at the point a comma f of a, the tangent is the line whose slope is actually equal to the derivative. That's not how it's defined. It's defined as the limit of secants, but then if you do the computation, that is what you'll get. That the tangent line is the line which passes through the point on the graph at A with slope equal to f prime.
Yeah,
So this
it's
is the
derivative.
equation of the tangent line. And if I just look at the corresponding function, so a straight line, as long as it's not vertical, and tangent lines cannot be vertical because f prime a is a finite real number whenever it exists. So if I look at the corresponding function, that is what is called the best linear approximation. So the idea is that if I have the tangent, if I have the graph of a function and the corresponding tangent line, let's say at this point, close to it, it models the behavior of the function fairly well. It is among all the linear function lines that pass through that given point, this is the best line, which gives minimum error. So if you want to predict just based on what the derivative is, as well as the function value is at a given point, this is the best function that you can use. All right, so that brings us to the end of the theory part. So now we can
Sir,
take questions.
I think we forgot that in that logarithm, I was forgetting that it will be base change rule. I think that's
Okay, the logarithm rules, I think some
in that
and
base
difference
change
was
rule. Base
written.
change rule.
Yeah. This one?
Yeah, if we convert to the in the base of 10,
Okay.
suppose we have a log base 3 4, then we have used to change in that form of log base 10. How we do?
Oh, okay. This rule that you're saying is log of a to the m is equal to log of some b to the m log of a to the base. This one, is this the one that you're asking for?
Yeah.
Yeah, but it is also there. Yeah.
Okay.
I think this was also not stated. All right. So this is also there. Yes.
Sir, while we are finding the limits, suppose if we want to find the left-hand limit, suppose let us take for an example, we are moving from point number 3 to point number 4. Do we have to take the value just before 4, right? So that is only the left-hand limit. That is,
Yes,
for
left hand
example,
limit, you don't
3.9.
say from 3 to 4. You say it is left hand limit to what? That is all that matters. Limit to some real number. So
That we
it
have to
doesn't
take
matter
that
that you're
point.
starting from 3. So because a sequence, when you talk about sequences, all that matters is what happens towards the end. So you have to just look at the immediate left of 4.
That is, suppose for example, let us take it as 3.9. At 3.9,
Okay.
what is the value? That is the left-hand limit of 4. Am I right, sir?
Not exactly what happens at 3.9. If you increase, like if you, as you get closer and closer to 4, 3.9, like for whatever reason, like it is 0.1 from 4, right? So is it near or far is not, there's no objective way to say whether it is near or far,
Okay, sir.
right? 3.99 is closer. Of course, if you have 100 more nines, that is much closer, but it is still very far from 4 from a certain point of view. So what is important is not what value is it is at 3.9, but as you increase from 3.9, the closer you get to 4, what value does the function go to? That is what is important.
Yes, sir. So in some
Okay.
of the graph of the function, there are some discontinuities in between. So in that case, we have to take the in that case, how to go about that, sir?
Okay, so suppose you have some graph of a function where you're interested at the point 4. You have some
Yes, sir.
discontinuities, I don't care. So this, whatever discontinuities there are, it's fine. As long as whatever its immediate behavior is, I'm only concerned about this part.
Okay, sir.
All right.
Okay, sir.
Sir, is the tangent equation of tangent and linear approximation are equals or different?
They are the same. So so one is a geometric object, one is a function. So well, mathematically there's a slight difference. But if you look at the geometric object, that is a graph of a function, and that function is precisely the best linear approximation.
Yeah, there is a question, sir, in which I told previously that continuity.
Okay.
Okay, there is a 1 minus cos 4x divided by x square.
The whole thing divided by x squared.
No, in the denominator.
Is this
If
correct?
x is yes,
Okay.
if x is less than 0.
Okay.
In that second line, a if x is equals to 0.
Okay.
In the third line, it is under root x whole divided by under root 16 under root x.
Under root 16.
Yeah, in that same root there is under root 16.
Is this it, or is there anything else?
No, you have written that under root 16 in that 16 multiply under root x.
Oh, something like this.
Yeah, then
Okay.
minus 4. No, in the denominator minus 4.
This.
Yeah. If x
Okay.
is greater than 0.
Okay.
Suppose that the function is continuous at x is equals to 0.
Okay.
Then we have to find the value of a.
Okay.
Yeah, that is the
So
question.
what is the right hand limit?
Is basically
So what is the formula that is applicable what I've written is correct, right? The definition of the
Yeah, basically this
function.
function is continued at x is equals to 0.
Okay, so it is given that it is continuous, right? Given
Yeah, it is given that, and we have to find that the value of a
f is continuous. So a
at x
necessary
at x.
condition is RHL.
RHL is equal to LHL, and it is equals to function of a.
No, but what is the value of the function at x equal to 1?
At x is equals to 0.
No, I'm asking, as per this definition, it would not work, no? At x equal to 1.
I think there is a. It is given that only that some data is available that continues at x is equals to 0. It is continuous.
Okay, that's fine. We'll deal with that. But what I'm saying is, if this is the expression for all x greater than 0,
Yeah.
then at x equal to 1, you will run into a problem. This will not be a well-defined function, because your denominator will become 0, right?
Yeah, it will be that.
So either the function itself is defined from, I don't know, -1 to 1 or minus infinity to 1, something like that. Okay, suppose let us just assume that at 1, there is no problem. The only problem point is 0. So
Yeah, is there
RHL
nothing
at
there is
0
nothing any
is
given that
equal to
limits
f
and
of 0 LHL at 0, right? This
yeah.
follows from continuity,
Yeah, it follows continuity that
right? So what is the right hand limit at 0?
the right hand limits that
So when you're talking about right hand limit, you have to look to the points which are greater than 0, right? What is the definition of the function to the right of 0 or at the part greater than 0? That is the third line, the third expression that is given, the last expression that is given.
yeah.
Now, what is the, if I directly substitute, what will I get?
Because when I think that I also not but basically it is a class 12th continuity chapters question. Even I don't solve it. So that's why.
No. What's the right hand limit? So now that we know some properties of limits, how would you compute the right hand limit for this function?
Yeah, it will be a big trap that.
This goes to 0, right? This part goes to 0.
Yeah, he'll.
So you'll just have -4 in the denominator, and this is 0 anyway,
Yeah.
right?
Yeah.
So the right hand limit is 0 from what I can see.
I think that
Isn't this 0?
question in that question some mistake. I think that's
There might be, because as it is not very difficult, because this guy has a limit 0. So automatically your question is easily solved. But let's just compute left hand limit also, because that is something that is more interesting. Now
yeah.
look at 1 minus cos 4x divided by x square as x approaches 0 minus. It really doesn't matter if it is 0 minus or 0 plus, it's both the same. So
Yeah.
what do you observe? So what happens when I substitute directly?
We get that
indeterminate form 1 0 by
that is also indeterminate that 0 by 0.
It is 0 by 0. So wait, let me just take it to the next page. So this is the guy that we are interested in. So we'll do two things. So how do I do this? So does this satisfy all of L'Hopital's conditions?
If we use then it will be plus sine. It will be 4 sine 4x divided by.
Does this satisfy the conditions where you can apply L'Hopital's? Yes or no?
Yeah, it is satisfied.
It is 0 by 0. Yes.
0 by
so
0,
we
yes.
can do that. So the fraction, the
4 sine 4x.
Ratio of the derivatives would be this by this, right?
Yeah.
Does the limit of this exist? Once again, this is in an indeterminate form. This is again 0 by 0.
Yeah, it will be again 0.
I can again apply L'Hopital's rule, right?
So
if we again use, then it will be become
Sir, can't we
minus
multiply by 4?
8x cos 4x.
Sir,
It will be-
can't we multiply and divide by 4 on the expression, sir? And directly
You
get 1?
can.
Now,
How
then
will we
after,
get 1?
then it will become 8. No, it
So
will
the
be,
limit of this is 8, right?
yeah.
8
I
is
think
the
that is,
answer.
yeah, I think that should be answer of A. A is a value of 8, yes.
Oh, right. Yeah. Then it has to be 8. So I don't know what
Yeah,
there must be
yeah,
some
sir.
mistake in the expression over here.
Yeah, yes, sir. But
What could
answer,
it be so that
then the answer, yeah, the answer will be matched, but I don't know that how to solve it. Then yes, I think that's correct.
A has to be 8 if you are looking at left hand limit, but right hand limit says 0. So I'm almost sure that there is something wrong with this expression. As it is, it
Sir,
cannot be continuous.
yeah, it will be some mistake on that. I think that's.
Yeah, RHL and LHL are not equal, so this cannot be continuous for any value of A. If this is the question as it is. Okay, and then there was so what were you saying? Multiply by 4.
No, that is correct. Yes.
No. This one is fine. There was another person who was saying, can we not multiply by 4 and continue?
Yeah, there is some girls speaking that.
Yes, sir. Me
Yes.
only, sir.
Yeah.
Getting the
Uh,
same answer, sir. Even
how?
if we
What did you do?
multiply and divide the numerator and denominator by 4. So
Of
sine
this
4x
expression?
by, oh, no, sir, below that.
Okay.
4 sine
Yeah,
4x,
that's
you
fine.
know that, sir. That,
Yeah.
that
That
tends
you
to
can
1, so.
Right.
Yeah, yeah,
That you can do. So here you
will
can
be.
do
Sir,
2 sine 4x divided by 4x and also multiply by 4 over here. And this part, as x goes to 0, goes to 1.
Yeah, it will be second approach that.
So this is 8. Now, even without using L'Hopital's in the first itself, using trigonometric identities also you can solve this. So what is cos 2x? This is
cos squared x minus sine squared x.
cos square minus sine square. There's 1 in terms of sine square, right? Like it's 1 minus 2 sine square, I think.
Yeah, it will be that. 1 minus.
So cos 4x will
1
be
minus sine
this.
square.
So 1 minus cos 4x is 2 sine square 2x, isn't it? So the original thing, I can transform this as 2 sine square 2x divided by x square. This is fine.
Yes,
Yes,
yeah.
sir.
Now I'll again multiply and divide by 4 to get 8
Then
sine 2x
divided
by
by.
2x.
Then it will
Whole
goes to
square.
1. Then also it is answer 8. Yeah.
This is also 8.
Okay,
So
sir.
there is
Understood.
not one method to solve the problems. There are multiple methods. And as long as you're verifying that the results that you're using are correct, like whether you can use
Yeah.
L'Hopital's rule, is it in an
Yeah,
indeterminate form? Then
the
the
result is
answers that you
correct.
get has to be the same, no matter
Yeah.
what the method used is. All right.
Sir, I have a
Okay.
doubt in one problem, sir. Shall I
Yeah.
share the screen, sir?
I don't know if you can. I think only hosts can. Is
Sir,
it from the portal?
yes, sir. Activity question number 2 from 8.1.
Number 2, 8.1. Just give me a moment. Okay.
In that, how to find the limits, sir? I mean, left-hand limit and right-hand limit. Here, we cannot fix the value, no, sir. That's what I asked the same doubt before.
The solid points denote the value of the function at the points, and the values denoted by the hollow points are not taken by the functions. Okay. What the question is? Okay. Let me try to redraw the graph roughly just for everyone else. So you have your function to be, so at 6, you have something like this, right? This, and then 2, it is solid all the way up to 4, which also goes to 10, something like this. And it's something roughly like this, right?
Yes, sir.
So this is at height 6, 4, 2, 0. And here the x coordinate is 2, 4, and all the way up to 10. Now, the options ask about left-hand limit and right-hand limit at the points 2 and 4. So
Yes, sir.
look at the point 2, the argument for 4 is the same. So here, whenever we're talking about limits, what the actual function value is at that point does not matter. That matters for continuity. It doesn't matter for limits. Now, to the right of, sorry, to the left of 2, this is the left of 2, right? Like the immediate
Yes,
vicinity is this
sir.
part,
Yes, sir.
right?
Yes, sir.
So what is the function value tending towards?
That is tending 10.
Sorry. Now, yeah,
It is
this
tending
height is
towards
10. It's going towards 10, right?
Yes, sir.
Yeah,
So
it is.
limit as x goes to 2 minus f of x, whatever this function f is, this is 10. Now,
Okay,
if I
sir.
look at the right-hand limit, I just need to look at the immediate vicinity after 2. What is the function value tending towards?
It is tending to 2.
Right. So you yourself have solved the problem now.
Yes, sir. But
Similarly, for 4, you just need to look at the immediate vicinity. Once again, the left-hand limit is 10 and the right-hand limit over here will be 4.
so essentially, we have to check whether the point before 2, am I right? Or point before 2, where it is approaching, that is the limit. Am I right, sir?
Yes. But so the point before 2 is not a thing, right? So there is no immediate predecessor to 2. So
Yes, sir.
if you talk about integers, what is before 2 is 1.
Yes, sir.
But
Yes, sir.
when you talk about real numbers, it is dense. It is densely
Yes, sir.
close.
Yes, sir.
So you have to just look at the immediate vicinity. That is correct.
Okay, sir.
But calling it just the point before is not the best way to state it.
Okay,
But you have
sir.
to look at the neighborhood, which is closest to 2 and to the left of 2.
Okay, sir. Thank you, sir.
All right. So I think we can close now. There must be other TA sessions, so you can take up problems there.
Yeah, sir, sure.
And if not that, then there's always discourse. You can post your doubts there. We'll stop now. All the best for the exams.
Okay, sir. Thank you, sir.
Yeah.
Thank you,
Bye.
sir.
Good night.
Thank you. Bye, sir.